Michelle Povinelli creates computer simulations that predict how light will travel through different materials, often in surprising ways. An assistant professor of electrical engineering at the University of Southern California in Los Angeles, she was chosen for this year's TR35 because her work will enable engineers in many different fields to make totally new optical devices. Some of her predictions are already being used to make fast, low-power optical switches with applications in telecommunications, while more recent work that studies how light moves through photovoltaic materials will mean more efficient designs for solar cells that could bring down the cost of solar power.
The thing I really like about the optics and photonics area in general is that it's an area where basic physics knowledge of electromagnetics and mechanics, is directly tied to applications. So an application area is that if we can do signal processing directly on photonic chips, we can eliminate some of these optical to electronic conversion and do it directly in the optical domain to eventually make the communication speeds or network speeds faster.
Eliminating the need to convert telecommunications data into electrical signals and back could speed telecommunications and make the internet faster. But it's a major challenge. One of the challenges in making photonic chips that can process light signals is that light is not as easy to manipulate as electrons. Povinelli is studying different types of structures that can be used to switch and manipulate light signals in much the same way as transistors manipulate electrical signals. Some of the most promising devices are photonic crystals.
This shows an SEM or scanning electron microscope picture of one of the devices that we make in our group. This is a silicon photonic crystal device. It's a piece of silicon with small holes in it, which are about 300 nanometers across. And we study how you can use the patterns of these holes to control where the light flows, and the speed which it flows, and the spectral response. In other words, what happens when you send down light of different colors, which colors make it through to the other side, and which ones are filtered out.
Povinelli is also studying even more unconventional ways of processing light signals. Light can produce mechanical forces that could physically alter photonic circuits in a way that allows for information processing. Povinelli has done pioneering work predicting these forces and designing devices that take advantage of them.
So one example that I look at is if you have light traveling in a small waveguide. So take my finger, imagine that's a waveguide. A waveguide is kind of like a wire for light, so if you put in light, it travels along. If you put two waveguides next to each other, it turns out that light traveling down these two waveguides can either pull the waveguides together or push them apart. And under certain circumstances, which we study, that force is large enough that you can actually observe this effect and then use it to control the behavior of other light traveling through your device. So you can use some strong light to move around parts of your device, and then a weaker light signal that comes along will then experience that change. And in this way we can, we call this an all-optical tuning scheme, because you can use one light beam to control your device or material, and that'll affect how other light propagates.
Povinelli's work will enable the development of devices that lead to faster, low-power telecommunications.